board. My first question is to review, what does it mean to solve a quadratic equation? It's a two-part answer. What does it mean to solve a quadratic equation? What does it mean to solve a quadratic? So if somebody walked up to you off the street or in cash cab or on $1 Million show, whichever, what would you tell someone is the meaning to solve a quadratic? And there's two parts. And here's a quadratic. It's ax squared plus bx plus c equals 0.
To find x.
To find x, that's true. Let's get a little more specific. What will x do for us? Once you find the right x, why is that x? Part of it is the x-intercept, and part of it is that it makes the equation true. So yeah, those are the two parts. First, find the number that makes the equation true. And second, which is the x-intercept? Find the number that makes it true, which is the x-intercept. So the x-intercept makes the equation true. All right. So how about the rest? What does it mean to complete the square? So here's an example. Let's say that I had x squared plus 6x plus, 6x plus 20. So this is the formula I give you. You might look at it first and say, can I factor it? Can you factor it? What two numbers multiply to make 20 to add to make 6? Nothing. So it's not factorable. So how would we complete the square? Or better yet, what does it mean to complete the square? This is a trinomial. How do we want to rewrite it? What's that?
Use the formula that you gave us to plug it in.
You mean the quadratic formula? It's not the quadratic formula. We're talking about completing the square.
So you divide it.
Right, so you do that check mechanism where you say, well, what number do I wish were right there? I take my 6, I divide it by 2, that makes 3, I square it, that makes 9. That's the number that I wish was right there. I wish it was right there, and so let's go ahead and do it. If I move the 20 over to get it out of the way, so now I have x squared plus 6x, leave a space, equals negative 20. I wish that that number was a 9, so I'm going to put it there. So I add it on the left, I add it on the right. Now, this is a very special relationship. What can I do with this trinomial now? What? How can I rewrite it?
X plus 3 squared.
Yeah, x plus 3 squared. There we go. So that's a huge deal. Right there, that's called completing the square. Going from a trinomial to a binomial squared is the process that's called completing the square. Why is it beneficial? Well, this is a trinomial, and just looking at it, it's really hard to know what x should be. You know, what number should I plug into x to make it true? We have no idea. Furthermore, there's no real method for solving that algebraically. It's not like a normal algebra equation like 5x plus 3, where you can say, oh, okay, sure, x is being multiplied by 5 and added by 3, so subtract the 3, and then divide off the 5. You know, we have a very specific, concrete way of doing algebra when there's only a single x. When there's an x squared, we don't have a normal, concrete way of doing algebra. We have to use these other techniques we've been learning. So x squared plus 6x plus 20, we can't do standard algebra on it. Instead, we have to either factor it, or now we know we can complete the square. Why is it better to write it like this than this? What can you do to this expression? What's quick and easy that you can do to this expression that allows you to solve for x? You can just square root both sides. That's wonderful. You can just square root, and then bam, that turns our previously x squared plus an x equation into simply an x equation. And now this we can just solve with standard algebra, right? We can just move the 3 over, and then we're done. X equals negative 3 plus or minus 11i. So it's just a random problem that I made up. But
You have to put the 11 under the square root. It could just be.
oh, you're right. Whoa, you can't really pull that 11 out. I root 11. Thank you. That's correct. So first question, what does it mean to complete the square? It means to take a trinomial and turn it into a special trinomial that can be rewritten as a binomial squared. And why is that the goal? Because a binomial squared can simply be square rooted, which gives you just a normal x as opposed to an x squared. So that's what this whole process is for. Completing the square is a process that allows you to take an x squared equation and turn it into an x equation. And then you can just do standard algebra. Okay, what are the steps of completing the square? Well, we just did them. You move the number term over, you do your check mechanism to find out what number you want to add, you add it to both sides, you rewrite the trinomial as a binomial squared, and then you just do normal algebra and you're done. So that's completing the square. How about the quadratic formula? What does it tell you? Yeah, exactly right, the x-intercepts. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's one thing it tells you. What's the other thing it tells you? The number that makes it true. So it's always both. It's always both. Whenever you find a solution, you're both finding a number that makes the equation true and you're finding an x-intercept. And that's what this formula tells you. It tells you the x-intercepts, which are also the numbers that make it true. Okay, and then what do you call the part under the square root? Did we already start talking about that? I don't know that we did. Did I call this anything?
No.
I didn't. Okay, that part right there under the square root is called the discriminant. And that's what we're about to start doing today. By the way, I'm very sorry. I think I'm losing my voice. So I know I sound awfully hoarse. I don't know if it sounds that way to you. I also bit my tongue, so I'm having a pretty bad morning. I'm losing my voice. My tongue is swollen. All right, let's do it. So here we are on April what? 19th? Yeah, this is April 19th. So you all just turned in your midway quiz. We've got 2 more days of chapter 10. On April 24th, you'll have a sub here with you. I think it's Larry T. Oh, I have it written down. Yeah, it'll be Larry Dieter is his name. I'm sorry if I said a different name previously. Larry Dieter will be here with you. He has taught this class before, so he's familiar with the material, and he'll be able to step right in and walk you through that day's worth of material. I also, let's see, I don't have it here with me, but the other night, this is really going to impress you. 2 nights ago, I sat at home with my wife, and we watched Labyrinth, right, with David Bowie. Came out in 1986, Jennifer Connelly, remember that movie? We watched Labyrinth, and while we did, I sat there and I filled out this entire packet by hand so that I could scan it into the computer, and I'll email it to you guys later today. That way you have all the solutions for all the problems in the packet, and that way you'll have that as well as Larry to walk you through the material. Labyrinth is just as good as it was 20 years ago, by the way, in case you want to go watch it. All right. And then next week, we'll come back, take a test, and then we'll get ready for our final exam. I can't believe the semester is already almost over. In my other class, we're starting a petition to extend the course through June. So if you guys wanted to sign that petition, we could just keep this course going all the way through the middle of June. Does anybody want to know? But it's strange, like 20 people in the other class are signing the petition. I don't know why you guys don't want to. All right, did I tell you my surrealist joke?
No.
Okay, so how many, now first of all, you know light bulb jokes, right? You know, how many so and such does it take to screw in a light bulb? Does anyone know a classic one that's like, you know, safe for class? No? Well, I just know one before I tell this one. How many Zen Buddhists does it take to screw in a light bulb? 2. 1 to screw in the light bulb and 1 not to screw in the light bulb. That's just a classic tenet in Zen, and everything is always oppositions, and doing something is not doing something. Okay, well, how about this one? How many surrealists does it take to screw in a light bulb? A fish. Yeah, it's not supposed to make sense. Kind of like the paintings of Salvador Dali, right? They don't really make sense. Everything's just wild. Okay. Well, that's it. So here we were. We just got to this problem, right? We were about to talk about the discriminant. It says use the discriminant to determine whether the solutions for the equation are 2 rational numbers, 1 rational number, 2 irrational numbers, or 2 non-real complex numbers, and also can be factored. All right, so I left you some space up at the top, and I did that so we could all take some notes together. All right, so you're going to have three cases. Case 1, case 2, case 3. So let's start by writing down case 1. So, case 1. What if when you're doing the quadratic formula, this part right here, the part that's underneath the square root's very important. What if the part underneath the square root, b squared minus 4ac, was less than 0? What does that mean? So the b squared minus 4ac, you compute it, and it turns out that it's less than 0, which means the number is negative. And that means we're square rooting a negative, and that means the answer is imaginary, right? So it means that there's an I involved. Now, an imaginary answer cannot be found on the number line. So what did that tell us about our parabola when the this part turned out to be imaginary?
It doesn't hit the X.
Yeah, it doesn't hit the x-axis. So go ahead and draw a little picture of a parabola floating above. So that's one thing we know without solving the entire quadratic formula. We call b squared minus 4ac the discriminant because it's a quick check. You could just take a formula and just grab the numbers b, a, and c and do this computation real quick, b squared minus 4ac, and just determine the nature of that number. And if it's negative, you automatically know that you're square rooting a negative, which makes it imaginary, which makes the parabola floating above the x-axis, which means there are no x-intercepts. So let's write that. No x-intercepts. Now, there's a bit of a paradox here because we said that the solutions to a quadratic are the x-intercepts, and we're saying there's no x-intercepts. Does that mean there's no solution?
Yeah. It's just imaginary.
Right, there is a solution, it's just imaginary. So remember, we've been talking about finding the number that makes the equation true. The number in this case that would make this equation true would simply have an I in it. So the solution would have an I in it. So there would still be two solutions that are imaginary. And that's kind of the main reason why imaginary numbers were invented. So remember, many hundreds of years ago, let's just say the 1500s, mathematicians wanted every equation to have a solution. And so they forced the issue and they said, hey, let's just make the square root of -1 count. Let's make the square root of -1 be a real thing. That way, even these equations would have solutions. That is, numbers that you can plug in to make it true. All right, so that's case 1. Case 2. What if b squared minus 4ac was not less than 0? What if it was equal to 0? So this part, right underneath the square root, is 0. What would that tell us? Yeah, there is one intercept. And so let's follow that chain of reasoning. What's the square root of 0? 0. And so let's just say, for the sake of argument, that it came out to be -5 plus or minus 0 all over, we'll just say 10. Well, what are the two alternate realities there? It's either -5 plus 0 over 10, or it's -5 minus 0 over 10. What do those work out to be? They're both just -5 over 10. Because adding or subtracting 0 doesn't actually change the value of the alternate realities here. So either way, the answer is just -5/10. So how many solutions are there? Just one. There's just one x-intercept. There's one number that makes the equation true. And so our parabola now looks like this, where it just barely touches down. It sits upon the x-axis at one number. So that tells us there is one x-intercept. More importantly, because the square root part went away, we're left with just a number divided by a number, which means the answer will be rational. There's no square roots involved in this number. It's just -b over 2a. That's just a pure fraction. So that means it's one x-intercept. That means there's one solution that is rational. And because there's no square root involved in the final answer, that actually means that this particular quadratic can be factored. That you didn't have to do the quadratic formula after all. You could have just factored it. So that's kind of neat right there. You know, at any given moment, if you're staring at a, oops, factorable. Let's say you're staring at a quadratic formula, like, I don't know, 2x squared minus 48x plus 72. You know, if you just look at that and I tell you, can you factor it? Well, you might have to stare at it for quite a while to figure out if it's factorable. You would have to sit there and think to yourself, well, let's make that a 1. 1 multiplies to make 72, that adds to make 48. It could take you a while to make the factor table, look through all the things that multiply to make 72, find out if any of them add to make 48. That would take a while. Whereas if you do b squared minus 4ac and you get 0, you automatically know that it is factorable, and you should spend your time trying to factor it. So that's kind of nice. All right, what's our last case? Either b squared minus 4ac is less than 0, or it's equal to 0, or yeah, it's greater than 0. Well, what does that tell us? If b squared minus 4ac is greater than 0, then that means you really are going to have a number here that you can square root. And so if there is a number right there that you can square root, what does that tell us about how many solutions there are going to be? You will have 2 solutions, because you really will have a plus or minus something. And that'll give you 2 different alternate realities. You're either adding that number or you're subtracting that number. So that it really is 2 solutions. So what does our parabola look like? Looks like that, where you genuinely have 2 solutions. So 2 x-intercepts, 2 solutions. Now, what do we know about those 2 solutions? What if b squared minus 4ac turns out to be a square number? Like, what if it was negative b plus or minus the square root of 100 all over 2a? That's kind of nice, right? Because can we square root 100? Yeah, we'll just get a number. We'll just get a normal old number like negative 5 plus or minus 10. And all of that is going to turn out to just be a normal rational number. So if b squared minus 4ac is a square number, then our final answer will be rational. No square roots involved. So if b squared minus 4ac is square, then the solutions are rational, and more importantly, it's factorable. So that's really exciting when b squared minus 4ac ends up being a square number like 100 or 25 or 36 or 49, because that means you can square root that number, and therefore there are no roots involved in your answer, and therefore you could have factored that one. That's one that you could have factored. And by the way, these 2 are related because 0 is a square number, right? We're saying that if that b squared minus 4ac is a square number like 16, 25, 9, 4, 1, or 0, well, 0 is also a square number, that's when a quadratic expression is factorable. What if b squared minus 4ac is not a square number, like 50? Then what are you going to be left with in your final answer? Yeah, you're still left with a root in your final answer. So if b squared minus 4ac is not square, then the solutions are irrational and it's not factorable. Well, Why do we even care if it's factorable or not?
Makes it easier.
Yeah, factoring is always going to be easier. Well, at least in my opinion, factoring is easier than completing the square or using the quadratic formula. So if you have a quick check way of finding out if something is factorable or not, I would just as soon factor it than I would do the whole quadratic formula or otherwise. So just for instance, that random x squared minus 48x plus 72 I put up there, I wonder what's that b squared minus 4ac? This is totally random, I just made it up. So b squared minus 4ac in this case is going to be negative 48 squared minus 4 times 1 times 72. So that's 48 squared minus 4 times 72. That's 2016. Well, 2016 is not negative. It's not 0. It's greater than 0. So now I wonder, is 2016 a square number or not a square number? I can just square root it on my calculator real quick, and it's not a square number. Therefore, I know that this thing is not factorable. I won't bother trying to ask what multiplies to make 72 that adds to make 48 because that's a waste of my time. And instead, I'll just do the quadratic formula. So that's what this is all about. B squared minus 4ac allows you to know ahead of time what kind of parabola you're looking at without actually doing the work. Okay. By the way, folks, what about this word discriminant? Do we use the word discriminant in normal everyday life? What word do we use that's similar to discriminant?
Discrete.
Oh, discrete? Okay, that's fair. Discrete, like something that comes in individual units.
Yeah.
What else? What other word sounds like discriminant? Yeah, discrimination, right? Discrimination, more or less on an everyday basis, is a bad word, right? Because you know, someone being discriminated against or an act of discrimination, that's typically a bad thing. However, the word discriminating is not a bad thing. I bet many of you have a discriminating taste when it comes to certain things. Like, I'm a pizza connoisseur, and I have a discriminating taste when it comes to pizza. This is good pizza. This is bad pizza. Have you ever heard that word discriminating in that context? I think I've heard it a lot when it comes to wine. People are like, oh, I know wine. I have a discriminating taste in wine. That's good wine. That's bad wine. So are you with me? Have you heard the word discriminating? Discriminating simply means to decide between two different things. That's good wine, that's bad wine, that's good pizza, that's bad pizza. So in that case, what does discriminating mean in this context? The discriminant is what discriminates between these three different cases. So we're not talking about being mean to people based on prejudice. We're talking about having a discriminating taste between the three different flavors of parabola. And that's what the word discriminant means. Okay, well, folks, let's try it. You've got how many different quadratics right there? 4? Yeah, 4 total. You don't even have to solve these, right? You don't even have to find a solution. You just need to do b squared minus 4ac and then figure out which case it is. So my recommendation for you here is to very carefully write down what a, b, and c are equal to. Like a is 1, b is -6, c is 5. You really have to be careful about the negatives, folks. I see a lot of times I see the common mistake that people just take the numbers 1, 6, 5. And that's not correct. You have to be 1, -6, and 5. And now plug that into b squared minus 4ac and see what you get. I recommend you all use your calculators. And just keep in mind, the b squared, what did I do to my b number right here?
Put a parenthesis.
I put parentheses on it because in your calculator, if you type in -48 squared versus -48 squared, this one will give you the wrong answer, and this one will give you the right answer. So everybody, let's go ahead and try all 4 of these right now with yourself or with your partner. Make sure you're doing your calculator correctly and that you put the b inside parentheses. And then see which of these 4 cases it is. Good question. Technically, the discriminant does not have the square root on top of it. The discriminant is not the square root of b squared minus 4ac. The discriminant is just b squared minus 4ac. But honestly, I find it helpful to remember that it's under a square root, because that's how I remember that when it's negative, it's imaginary, because I'm remembering that, oh, that means I'm square rooting a negative, that's imaginary. So the discriminant technically does not have the square root on top, but it's helpful to think about the fact that it has a square root on top. Ultimately, the discriminant is the number under the square root.
I just want to say that. And so what is that? Yeah, and that's what people all you can do is do right now is just go see students. You don't even have to do that. Because right now we're not we're just using the discriminant to start next axis. Yeah, so you don't have to do the extra.
I see a lot of you getting 16 for the first one and 0 for the second one. You just want to check so far with the first and second solution. I see 16 and 0.
So this one actually puts in parentheses. Not the square, just yes, it's negative. So negative. All right. This is very nice. You're showing the whole solution. You don't have to do the whole solution right now. I'm just looking for that number 6.
Okay.
So you can save yourself the work.
Okay.
So you just have to calculate the part underneath.
You can feel free to do more if you wish. You just don't have to.
That's, and so you don't have to do all the whole problem, just the b squared minus 4ac. So you're just looking for that number under the square root, right? Okay. Yeah, not asking to solve the whole thing. You can just do b squared minus 4ac and see what that number is.
Yeah, there you go. That's the number 16. Okay. Is that 57? I think I'm seeing the third number is 57. Is that what everyone has so far? 16, 0, and 57. That looks to be like the first 3 solutions. What's that?
So plus, wait, b squared minus 4ac. Yeah, the formula is b squared minus 4ac.
There you go.
That's it. That'll change that. This is very nice. You saw it. Just for right now. This page only, we're just solving b squared.
Turn around, I hear 16.
You sure did. I see that. Well, it's b squared minus 4ac. And so b squared is negative 2, and then minus 4a times b is 5. You gotta come up here.
Yeah, so it's just 1.
Yeah, it's just a 1. There you go. The brain, that does that to us sometimes.
All right. since everyone has their notes written down, I'm going to erase mine and look at these problems, and we'll interpret them. So we have s squared minus 6s plus 5. And so b squared minus 4ac would be negative 6 squared minus 4 times 1 times 5, which is 36 minus 20, which is 16. That's a great answer, because 16, first of all, it's positive. So in this case, 16 is greater than 0. That means we're looking at this case 3, right? So everybody, for this particular one, go ahead and write the word below to kind of give you that gut conceptual understanding that if the number is positive, that actually means the parabola goes below the x-axis, which gives you 2 solutions. Furthermore, how about the number 16? Is it square or not square?
Square.
It's square. That tells us that our 2 solutions are rational, because you can square root 16, so there's no square roots involved in the answer, so it's not irrational, it's rational. And furthermore, 16 is backwards. So back to this. S squared minus 6s plus 5. Is that s minus 5 plus 1? Provided that the discriminant turns out to be a square number, this thing should be factorable, and it is. So that's the first one. T squared minus 2t plus 1. In that case, t squared minus 4ac was negative 2 squared minus 4 times 1 times 1, which gives us 4 minus 4, which is 0. So that one, because it's 0, what do we know about our parabola?
0 on the
X-axis.
Yeah, it's actually just sitting on the axis. It's sitting right on the axis. So there's just one solution. So we know that it's one solution. And furthermore, is 0 a square number? Technically, 0 is a square number. 0 times 0 is 0, so it's a square number. That tells us the same thing, that the 2 solutions are rational and that this quadratic is factorable. And sure enough, t squared minus 2t plus 1 is t minus 1 times t minus 1. So it is factorable. How about the next one? V squared plus 7v minus 2. What did you all get for the discriminant value? I'll just go ahead and skip to that. V squared minus 4ac is 57. All right, so 57. First of all, 57 is positive, so what does our parabola look like?
Below.
Yeah, it's below. There are 2 real solutions. Oh, by the way, I should have said for this one, on. So here, the parabola is on the x-axis. Here, it's below the x-axis. Here, it's on the x-axis. This one's below the x-axis. Now, 57, is that a square number?
No.
It's not a square number. So when you put that underneath a square root, you're going to end up with an irrational number. And so these 2 solutions are irrational. And since it's irrational, is this quadratic factorable?
No.
It's not factorable. And in fact, you can kind of tell that already. One number is multiply to make 2, and add to make 7. Well, nothing. Nothing will multiply to make 2 is going to add to make 7. That's not possible. So that tells us that as well. So how about the last one? We've got w squared minus, I ran out of space. W squared minus 5w plus 7. What did you get for that one, folks? Negative what? 8? So, oh, negative 38. Okay, well, it's negative. That's all we need to know. That is when you do the...
It's negative 3.
No, negative 3. Boy, I cannot hear. Negative 3. So that tells us what about our parabola? It doesn't intercept, so it's above. That parabola is above the x-axis. Therefore, there are solutions, but they're imaginary. And that's all you have to say. 2 imaginary solutions. Now, here's an interesting question. Can an imaginary solution be rational or is it irrational? So for instance, let's say that the solution turned out to be x equals 4i. Is that rational or irrational?
Irrational.
Why irrational?
Instead of I.
Right? What makes I irrational? It's a root. Yeah, it's a root. It is imaginary, that's true. But remember the definition of irrational. Irrational is any square root that doesn't simplify out. So irrational would be like root 5, root 6, root 7, any root that you can't actually simplify down to a whole number. And irrational number is the square root of a number that's not square. And -1 is not a square number because there is no number that multiplied by itself gives you -1. So since this is not a square number, that automatically makes the square root of -1 irrational, which makes any imaginary number irrational too. So when we say it's two imaginary solutions, technically those are irrational solutions. Not that it really matters. You know, that's really technical. All right. Well, folks, on your test, what I would like to do is I will give you 3 quadratics, and one will be case 1, one will be case 2, and one will be case 3. And what I'd like to see from you for those 3 problems on the test is you'll be able to use the discriminant, just the discriminant. You don't have to calculate the whole thing. You don't have to calculate the x-intercepts. You would just have to tell me if it's above, then you would say above and draw a little picture and say imaginary. If it's on, you would say on and say one rational solution. And then if it's below, then you would say below, and you would tell me 2 rational solutions, which means it's factorable, or you would tell me 2 irrational solutions, and if it's not factorable. All right, so that's what full credit would look like on those questions on the test. You'd be telling me the word above, on, or below, and you'd be telling me the nature of the solution, whether it's imaginary, 1 rational, or 2 rational, 2 irrational, and factorable. Questions about that? Notice that's a lot of information you know about a quadratic without even finding the solutions. Right? We haven't even found the solutions yet, but you know the nature of the solutions. And that's what makes the discriminant so neat. You know, neat. All right. This next section, if you take a look at what it says in the instructions, 10.4, equations that will become quadratic in form. So we're not going to solve these together in class. You can solve them yourself. I'm just going to show you how to convert them into a normal quadratic. Because once it's a normal quadratic, you can solve it yourself using the techniques we've mentioned. So looking at the first one, is that your number 31?
Yeah.
Okay. So 1 minus 10 over x minus 24 over x squared. Is that a quadratic equation?
Not yet.
Yeah, no, not yet. And it's definitely not as it is. You know, a quadratic is ax squared plus bx plus c. That one, where's the x squared? It's in the denominator, right? That's very different. Just to show you how different it is, what do you think that graph looks like? Do you think it looks like a parabola? Let's find out. 1 minus 10 over x. Whoop, so far not looking good. Minus 24 over x squared. Aha, that's our graph. Does it look like a parabola? Not at all. Definitely does not look like a parabola. However, are there x-intercepts?
Yeah.
Yeah, there's 2 of them. And the fact that there's 2 of them means that there's something about this that could be a parabola because there's 2 solutions. So you can imagine that the parabola is right here. That is a parabola that has the same solutions as this equation. So we're going to leave that graph up for a second as we go ahead and manipulate this equation, and then we'll see what happens. So our equation was 1 minus 10 over x minus 24 over x squared equals 0? Okay. So who remembers the procedure for this? We want to get rid of all the denominators. How do we get rid of denominators? You could use the spoiled child theory. By all means, you definitely could. Another thing I heard was get rid of them. I like the idea of getting rid of them. How do you get rid of denominators?
1 over 1.
Well, sure, yeah, we can start by putting 1 over 1. So this is really 1 over 1. And how do we get rid of a denominator? So Brandon, doing the spoiled child theory, that would give us common denominators, but it wouldn't get rid of the denominators.
You multiply the denominator by itself.
Multiply the denominator by itself. I don't know if that would work. And plus, you can't just multiply the denominator by itself out of nowhere.
But don't. Oh, you gotta multiply to the other side as well.
Do you mean multiply both sides?
Yeah.
That's true. That's part of it. What do? We need to find the. Well, okay, Brandon, back to you. We do need to selfish child theory to find the lowest common denominator. That's true. We do need to find the least common denominator. What is the least common denominator in this case? This child has a 1, this child has an x, this child has an x times an x. So he's jealous of both of them because he doesn't have any x's at all. So I need to give him 2 x's so that he's like this guy. This guy only has 1 x, so he wants another one. So I'm going to give him another one. So what's the common denominator? X squared. Yeah, so the common denominator is x squared. And now what do we do with that common denominator? Yeah, we multiply it all the way across. So that's what we did in chapter 7. To be fair, that was 2 chapters ago. Remember in chapter 7, if we wanted to get rid of a denominator, you would multiply all the way through by the lowest common denominator, and that would have the effect of canceling all those denominators. Brandon, is that what you meant when you said selfish child theory? You're absolutely correct. So let's try it. I'm going to multiply across that x squared. That gives me 1x squared over 1 minus 10x squared over x minus 24x squared over x squared equals 0. 0x squared, which is still 0. Now what? Now that we multiplied all the way through by the common denominator, what can we do?
What's that?
Yeah, we can cancel. I can cancel 1x here. I can cancel both x's here. And so what are we left with? X squared minus 10x minus 24. Now I'm going to stop right there. You, for your homework, proceed to finish that problem. I imagine you can all finish it right now because it's factorable. So you can factor it real quick. But now let's look at the parabola. X squared minus 10x minus 24. Take a look. Does the parabola have the same solutions as that original funky curve?
Yes.
Yeah. So this is interesting. In mathematics, if we're presented with an equation that we don't know how to solve, like the original one, which has this funky red graph, what we can do is manipulate the equation and turn it into something else, which now is just a blue graph, my blue graph here, which is just a parabola. And the parabola I know how to solve using either factoring or the quadratic formula or completing the square. So I have to say that's very clever in mathematics, that you take an equation that you don't know how to solve and you manipulate it and turn it into an equation you do know how to solve. And graphically, even though the two graphs look different, they have the same x-intercepts, which means they have the same solutions. So by solving this equation, okay, I can't help myself. By solving this equation and noting that x equals 6 and x equals, did I do that right?
I think that should be a positive 24, right?
I didn't do that right. It's 10 and 2. I'm sorry, it's 12 and 2. There we go. X minus 12, x plus 2. Ha, I almost factored that wrong. There we go. So now I know my solutions are 12 and negative 2. And that is what the graph shows. The x-intercepts are 12 and negative 2. And so the solutions to this quadratic parabola are the same solutions as the solutions to the original function, which was not a quadratic. All right. Well, that's it for that graph. So let's try that again. The next one is 3 over 3x minus 3 over x plus 1 equals 1 over 1. I'll just go ahead and write it out as 1 over 1. Because we know it's rational, we're going to have to find a common denominator. So what does selfish child theory tell us about the common denominator? What will our common denominator be? Every child is going to want,
Yes.
yeah, the 3x and the x plus 1. So that right there is our least common denominator. Because that kid has a 3x, that kid has an x plus 1, that kid has nothing. So all three denominators are going to want a 3x and an x plus 1. So now, this part, you can show all of your work like I just did here. I showed my work of actually distributing the x squared and then canceling it. If you can see how to do it in your head, that's fine too. I would give you full credit on a test. So for instance, right now, when I multiply this times 3 over 3x, what's going to cancel?
3x.
The 3x. So now I know I'm just multiplying 3 times x plus 1. You can do that part in your head. You don't have to show the work there if you don't need to. If you still want to, that's fine. You can. I'm just saying I won't take off any credit if you do this in your head. Likewise, for the next one, when I multiply this times 3 over x plus 1, what cancels?
X plus 1.
The x plus 1 cancels. So you're left with 3 times 3x. And then finally, when it multiplies all the way over to the 1, nothing cancels, and I have 3x times x plus 1. All right, we effectively canceled the denominators. That means this is now just a normal equation. And as soon as you distribute combined like terms and put it in standard form, it's a parabola. It's a quadratic. So let's do that. Distribute. That gives us 3x plus 3 minus 9x equals 3x squared plus 3x. What can I do right now? Even before I combine like terms. Is there anything I can cancel?
3x.
Yeah, I can cancel those 3x's. Might as well do that. Okay, so now, yes, I want to move my terms over. With the 3x squared, so I'll minus my 3. I'll add the 9x. And that gives me 3x squared plus 9x minus 3 equals 0. And I think that's where I'm going to stop. Because we've done it. That was the main point of this problem, is the ability to transform an equation that's not quadratic and turn it into an equation that is quadratic. And so we've done it. At this point, you would just solve that using all the methods that we've talked about. You might factor out a 3 first, and then you might do the quadratic formula. You might try to factor it. You might do completing the square. You can do it however you like. Just to show you again how clever this is, and maybe when I use the word clever, you're like, Mr. G, this is not clever. This just is, math. But it is nevertheless clever that a mathematician at some point in time said, hey, you see this equation? Look at it. That just looks like 2 vertical lines. 3 over 3x minus 3 over x plus 1. And what did we do? We transformed it into 3x squared plus 9x minus 3. Oh, how strange. There we go. So the green one, whoo, look at the original graph. It's all funky. It's got lots of different parts to it. It's curvy in a strange way. And yet it has 2 x-intercepts, which makes you think it could be modeled by a parabola that has the same x-intercepts. And sure enough, there's the parabola. So this is the parabola that we just came up with, which goes through the same x-intercepts as the original graph. So again, in mathematics, this is what we call taking an equation that we don't really know how to solve and manipulating it into an equation that we do know how to solve. And so the parabola and the original both have the same x-intercepts. Okay, well, I'm going to leave that last one for you, number 33. Or to tell you the truth, you can just cross it out. Because you'll have one like this on my math lab. And so that's probably enough practice. So you can cross out number 33. All right. So we have some word problems to solve. These will look similar to what we've done in the past, but they're slightly different and a little more challenging than what we did before. So let's just read it once. Working together, Rick and Juanita can complete a job in 6 hours. You remember this one. It would take Rick 9 hours longer than Juanita to do the job alone. So how long will it take Juanita alone? Well, first, let's just remember how a problem like this was done. You remember before we had a problem where Susie could do the job in, say, 2 hours, and her little brother Billy could do the job in 6 hours, and we wondered how long will it take them to do the job together? So first of all, approximately what's the answer? If she can do it in 2 hours and he can do it in 6 hours, how long will it take them if they work together?
1.5.
Yeah, like maybe 1.5. It's got to be less than 2, right? Because Susie's getting help. So if she can do it alone in 2 hours and she gets help, it's going to take them together less than 2 hours. So we know the answer is 1 point something. Well, so now do you remember how we set it up? We did Susie can do one job in 2 hours, whereas Billy can do one job in 6 hours. And then what we did was we attached the variable t to both of them to account for how many hours have gone by since they started working. And then we set that equal to one job total. This was the setup we did before. So I'd like us to generalize that. What this is 1 over the first person's rate, so we'll call that rate 1, times the variable t, plus 1 over the second person's rate, we'll call that rate 2. And the important thing to note is that this rate is the first person's rate, this rate is the second person's rate, and t represents time together. So t is time together. As in how many hours it takes for them to finish the job together. So we could call this the general formula that we're looking at. That's how you set up all of these problems. So now let's go back to look at Rick and Juanita. I'm going to go ahead and write down my formula. So that's 1 over rate 1 times time plus 1 over rate 2 times time should equal 1. So if that's the formula, what do we plug in and where? So it says here, Rick and Juanita can complete the job in 6 hours together. Where do I put the 6?
For rate 2?
No.
Rate 1?
No.
For the one time.
Not where the 1 is, for the time. We put that in for t, because t is time together. How long it takes them to do the job together. So I'm going to go ahead and I'm going to write this kind of very open here. 1 over something times something equals 1. So in for the t, I'm going to put 6. And I'm sorry, maybe I didn't define that well enough. Again, the t represents how much time it takes them to do the job together. So now it says it would take Rick 9 hours longer than Juanita. So let's agree that this is Rick, this is Juanita. So how do we write that down? Rick will take 9 hours more than Juanita.
X plus 9.
Yeah, this would be x plus 9, and that would be x. So we don't know what Juanita's rate is. I'm going to say it's x. And if Juanita's rate is x, then Rick is 9 hours more than him, so that would be x plus 9. And that's actually it. That's our setup. I'll bump the 6 into the numerator where it belongs. So that's 6 over x plus 9 plus 6 over x equals 1. That's the equation to solve. Notice the question is even asking, how long will it take Juanita to work alone? That's what x is. X is Juanita's rate. So by the time we're done solving for x, that is actually the answer we're looking for. So how do we solve this? Yeah, we want to cancel the denominators by doing the exact same technique we just did, by multiplying through by the common denominator. So our common denominator is?
X plus 9x.
Yep, x times x plus 9. And we multiply that all the way across and transform this rational expression into a quadratic that we can then solve. So we'll do this one all the way together. I'll go ahead and multiply that across. So there, there, there. So here the x plus 9's cancel out, that gives us 6x. Here the x's cancel out, that gives us 6x plus 9. And then over there, nothing cancels out, it's just x times x plus 9. So right then, by multiplying through by the common denominator, I just transformed what the graph would look like. Originally, the graph was some funky looking graph with asymptotes. Whereas now that I multiplied through by the lowest common denominator, now this is just a quadratic, so it looks like a parabola. But the original funky graph and the parabola will have the same x-intercepts. So by solving this problem, I'm getting the solutions to this problem. So we distribute. 6x plus 6x plus 54 equals x squared plus 9x. We did not luck out to have anything to cancel this time. So we just have to combine like terms and then move everything to the right. So 12x plus 54 equals x squared plus 9x. Move the 12x. Move the 54. And that gives us x squared minus 3x minus 54. Now, I imagine that many of you are thinking, hey, I wonder if that's factorable, because if it's factorable, we can just factor it. And maybe you already know the answer because you're thinking about what multiplies to make 54. But just for fun, let's do the discriminant. I just want to show it to you. B squared minus 4ac. B squared, that's negative 3 squared, minus 4 times 1 times negative 54. That's 9 plus 216, which is 225. And what do you notice about the number 225?
It's squared.
It's 15 squared. So yes, this is factorable. Now, whether or not that was worth the effort to realize that this is factorable, because maybe you already know what multiplies to make 54 that adds to make 3. 9 and 6. So that factors into x minus 9, x plus 6. And so the answer is x equals 9 or x equals negative 6. Are both of those solutions relevant to this problem? Just the positive one. Yeah, because it doesn't make any sense that Juanita takes negative 6 hours to do a job. So negative 6 is extraneous. So you'd say extraneous. And the 9 is the answer for Juanita. So Juanita takes 9 hours. And how long does Rick take? 18 hours. And working together, it takes 6 hours. All right. Well, number 35 is just like it. So I'm a little torn as to whether or not we should do it together or move forward. I think move forward. Yeah, I think I'm going to say number 35 is literally just like this one. So you can model it just after this one, and you'll walk yourself through the same steps. So you can do 35 on your own, and let's go ahead and take a break. times 902. Let's come back at 912. What? Do I have the tests?
Yeah, the one from last week. So I wasn't here on Tuesday, so I don't know what happened.
Oh, I did hear. Boy, I was getting all nervous. Like, oh my gosh, did you guys take a test and I haven't graded it yet? One. Or junior. Actually, I'll let you. Did you take it here in class?
Yeah.
Or in the one exam?
I took it.
Are you sure you didn't get back?
No, I'm sure. I don't know if you graded it. I can check.
Oh, I got nothing. I don't have it in my folder.
You want our midway quizzes?
Yeah, I collected them at the beginning of the class. Okay. Here, is that it? Let's,
Is there one with no name? They remember doing it.
there's not one with no name. Maybe I accidentally passed it back to someone. So you don't have it?
I don't.
Well, this is an issue. Let me see if I gave you a grade.
Okay.
Austin, here's your test. Jackie, here's your test.
Oh, no, not chapter 10.
Chapter 9.
Yeah.
Oh,
You gave me a grade.
I did?
Yeah, 74.
Okay, that's sounds right. But my only thought, Elda, is that it might have stuck to someone else's.
Oh.
So I'll ask everybody if anyone has a memory of that. Elda, I'm so sorry. I can't imagine how this happened.
On Tuesday, that's today we're having sub, right?
Yeah.
Yeah, because I might be in California. My grandfather's sick, so no one wants to go visit.
Okay.
This is for the absences. If you have a doctor's note, would you not count as an absence?
The policy doesn't distinguish between excused or unexcused absences. I'm not gonna punish you extra for unexcused or excused or anything. It's just you were either here or you weren't here. Yeah. But that's why everybody gets 2. You get 2 absences, 2 tardies before I start taking off once. Yeah, so I mean you get 2 freebies. 4 freebies really.
I did not know that.
So Elda, you took it here in class.
Yeah, I did it. I was in the back. And
Okay. And I gave you a grade.
that was the thing.
So maybe it's in another folder in my backpack, or maybe I accidentally gave it to someone. I will ask everyone to check.
I mean, no hurry. I just.
Well, heck, you deserve to have your test back. It's yours.
I mean, I haven't realized that's good.
Yeah, thank goodness you have a grade. I've always had a nightmare. Like, let's say I was driving home and I got in a car accident and all my papers flew out of the freeway and they were just gone. And so, like, some number of students who worked so hard to take a test, I wouldn't have their test anymore. And in that story where I'm in a car accident, my car rolls and all my papers fly out, that's the worst part, is that I lose students' papers. Yeah, forget my car, whatever, it's the papers. How terrible.
It's okay, we find.
Thank you.
I feel much better. Yeah, I love it that.
What did you eat?
I don't know. I ate normal food and I got super sick. It was like Monday. I felt so sick. I got 4 minutes and so I couldn't stop. So I got to the died. Into the urgent care. They gave me national medication, some shots. I was like, when I was home, I still could. And the next day, I was feeling the same. Like I couldn't eat anything. Yeah, it's so. It's so bad. But I'm okay now. I showered, I'm fine. I'm not, making me sick. It's just my stomach is heavy. Sorry. Maybe soups. But yeah, it was great.
I like the coconut.
Oh, thank you. Actually, changed colors. Touch it.
My friend has that,
Mhm.
the little doorknob thing.
Oh, I know. I never usually use that. But then I just got it because I thought it was cute. And it's cool. And I feel like I need so much to go to my psychology class, my English class, and I come here. But my psych teacher was like, let's just get better. We're watching a movie. Did you work this? Oh, you work all week, right? No. Did you do your something already?
I want to go talk to the advisor that she has been mentioning for the 3 days.
Oh,
Yours.
I don't know.
And she's
I'm doing it like once. That's it. And then since then I've been walking under. She gave me like the other one to take. I didn't take it. I don't know if it's changed. So I've been there. I've been serious. Oh, thanks. Never, yesterday I kind of felt okay, but I was like, okay, I have to go to get my second What is it?
I'm tired.
Yeah. I know you.
I'm bad. Makes you whole bad. I look tired.
Yeah. Like, because of your eyes, it's Yes. No way. I work tonight, so.
I just used to very excited. Really play stuff. As long as you as long as it's out of water. Is that? Oh, maybe one. This is in your touchdown.
I didn't get it.
I'll be a math teacher. So I'll be a math teacher.
It's just-
The only thing I don't want to do is make stuff. That's a funny
Yeah, I don't know.
All right, folks, let's keep going. I hope everyone's back. Come on back, folks. All right. So we just finished the working together problems. Another type of problem you have is rate problems, where something is flying with the wind and then against the wind, or going upstream and then downstream. So let's review how to set that problem up as well. So number 36, it says a jet plane, not just a plane, a jet plane. Whatever that means. What's the difference between a plane and a jet plane? I guess it's not a propeller plane. That's an important distinction, son. Yeah. So a jet plane traveling at a constant speed goes 1,200 miles with the wind. So let's draw. So we've got this is the wind. And first the jet plane goes this way, so with the wind. And how far does it go? It goes 1,200 miles. Oh, by the way, keep in mind, we're using the formula D equals RT, which can be manipulated to look like T equals D over R. Right, that's the fundamental formula we're using, is distance equals rate times time, which could be rewritten as T equals D over R. So the jet plane goes 1,200 miles with the wind, then turns around and goes 1,000 miles against the wind. So that time his D is 1,000. What do we know? It says if the speed of the wind is 50 miles an hour. So let's just make a mental note. The wind is 50 miles an hour. And the total flight took 4 hours. Find the speed of the plane. Okay, we still have a lot left to write down. But first of all, what are they asking us to find? The speed of the plane. So let's go ahead and say let x equal speed of the plane. Oftentimes, we have to figure out what variable to use and what to let it represent. The variable should always represent what the question is. So whatever the last part is, the question, find the speed of the plane, that tells you right there that your variable should represent the speed of the plane, because that's the unknown that we're trying to solve for. So if x is the speed of the plane, then what is the rate of the plane with the wind?
X plus 50.
Yeah, x plus 50, because the plane is going with the wind. So it's picking up an additional 50 miles per hour. Whereas what's the rate going against the wind? Yeah, x minus 50. Because the plane itself is going x miles per hour, but it's going against the wind, so it's losing wind 50 miles per hour. All right? All right, we almost have all the information from the problem. Folks, keep in mind, reading a word problem and writing down your work, it takes multiple passes through the word problem. Sometimes you have to read the word problem 2, 3, maybe 7 times. So let's just check. A jet plane traveling at a constant speed goes 1,200 miles with the wind, then turns around and travels 1,000 miles against the wind. If the speed of the wind is 50, okay, and the total flight took 4 hours. We haven't used that information yet. We haven't used the fact that the total time is 4 hours. Find the speed of the plane, which is x. So what's the last piece of information we need to use?
Time.
Yeah, the 4 hours. Now, what does that mean? We're saying that time total is equal to 4 hours. Well, how do we use that?
Divided by 2 equals 2 hours.
You're saying divided by 2 because it's 2 hours this way and 2 hours this way?
Yeah.
That's an assumption that it was the same amount of time both ways. After all, he went further here and less distance here, so maybe it's not the same time, right? So what else can we do? It could be 2 different equations. What's that, Brendan?
Like
Add them together. So like you want a total of 2,200 miles? And you want a total of, or 2x was your rate? Maybe? Maybe? Any other thoughts? This is good, brainstorming. You know, you just throw out ideas and
Or do we just use E equals RT and then just put the 4 parentheses?
right, maybe throw in 4 for the time there. Maybe. Well, we know the total amount of time. Do we know how much time this took? We don't. Do we know how much time this took? We don't. But we know that this time plus this time equals 4. So that's actually an equation right there. I don't know how much time this took. I don't know how much time this took. But if I add this time plus this time, it should equal 4. So let's write that down. Let's write time with the wind plus time against the wind should equal 4. How's that? Is that a true statement?
Yes.
Well, do we know how much time it took to go with the wind? We don't. However, do we know a formula for time?
Yes.
Do we know the formula is d over r? And for with the wind, do we know d and r?
Yeah.
We actually do. So now what we can do is, instead of time with, we can say d over r with the wind plus d over r against the wind should equal 4. By the way, this was the ultimate formula. I wrote down the time total was 4. That was just writing down some notes about what's happening. This is the actual formula that's going to drive our problem. Remember how long ago I said there are 4 steps to a word problem? The first one is drawing a picture, which we did. The second step is making an equation, and that's our equation. The equation is that the time with the wind plus the time against the wind should equal 4. So now we plug everything. Let's go ahead let's plug everything in. So the first one with the wind is what? 1200 over x plus 50. And then the time against the wind was 1000 over x minus 50. And that should equal 4. Have we solved an equation like this today? Yeah, we did. We have solved an equation like this today. We would use selfish child theory to think about what the common denominator is. What's the common denominator going to be?
X plus 50.
Yeah, x plus 50, x minus 50. And we'll go ahead and distribute that across, and then we'll have an equation. Before I do that, I just want to point out that there's, getting an equation, now we can just solve the equation. But getting to that point was fairly challenging, wasn't it? It wasn't obvious how to put this information together. And that's kind of one of the other big skills you're learning is how do I take a word problem, figure out what it's saying, and then come up with the right equation to use. It takes a lot of practice to be able to do that. All right, so now we just multiply across. What cancels in the first one?
X plus 50.
Yeah, x plus 50. So now that's 1200 x minus 50. What cancels in the second one?
X minus 50.
The x minus 50, so that's 1000 x plus 50. And then all the way on the other side, you have 4 times all of that. So that's 4 times x plus 50, x minus 50. It's a doozy, right? We still have quite a bit of work left to do in terms of distributing. We get to FOIL, x plus 50, x minus 50. So we have 1200x minus what? 60,000?
Yes.
And then plus 1000x plus 50,000. Now, before I multiply 4, what do you notice about x plus 50, x minus 50? Yeah, the middle terms will cancel out because these are conjugates. This is actually the difference of squares formula. So that's really x squared minus 2500. If you just multiply 50 times 50, you should get 2,500. So that's the difference of squares formula. Okay. So now on the left-hand side, we can combine terms. What does that give us? 2,200x minus 10,000 equals 4x squared minus 10,000. Am I doing that right? Is everyone in agreement? All right, well, I'm obviously out of room, so I'm going to finish my problem up here.
2,000.
What can you do with the 10,000s?
Cross them off.
Yeah, you can cancel them out. There's a negative 10,000 on both sides. So we cross those out. And so what we're left with is 4x squared equals 2,200x. Folks, am I allowed to do that? I just reversed my equation. It was 2,200x equals 4x squared. I wrote down 4x squared equals 2,200x. Am I allowed?
Yes.
Yeah, I just reversed it. Okay, how do we solve that?
Square root.
Well, you could divide by 4. You could try to square root both sides, but that won't work out because this is not square rootable.
For ABC.
It's always helpful to put everything on one side of the equation and set it equal to 0. That's almost always the way, is to make it in standard form. So I'm going to bring the 2,200x over to this side. And that gives us 4x squared minus 2,200x equals 0. I would say that's a good strategy in general, folks. If you're ever not sure how to solve an equation, put all the terms on one side and set it equal to 0. Because now what can we do? Yeah, what can we factor out? A 4 and an x. So that gives us x minus 550. Is that the correct factoring?
Yeah.
All right, well, finally, we have a zero product rule. So either this equals 0 or this equals 0. If 4x equals 0, what does that mean about x? X is 0. If x minus 550 is equal to 0, what does that mean about x? 550. So remember, x is the speed of the plane. So is the plane going 0 miles per hour? Probably not. So the plane is going 550 miles per hour. So this solution is extraneous, but the 550 is correct. And that's what we were looking for originally. The speed of the plane is 550 miles per hour. Now, how do we check our work? Other than looking at it in the back. Yeah, you plug it in to where?
Original.
The original, always the original. So let's just do a quick check. If I put 1,200 over 550 plus 50 plus 1,000 over 550 minus 50, does that equal 4? This is 1,200 over 600. And this is 1,000 over 500. So you know you're going to be really excited. What's 1,200 over 600?
2.
And 1,000 divided by 500? So you know, what does that tell us about the time with the wind and the time against the wind?
Same.
It did end up being the same.
I was right.
But we had no way of knowing that ahead of time, right? So yeah, you were right. But, you know, we just couldn't have known that ahead of time. Yeah. All right, so it did work out and we got it. That's a monster of a problem. I recommend you all go home and do that problem again, probably twice. Do it at least once more just to see the whole flow of how to start it off at the time with, time against, t equals d over r, plugging in all the numbers, doing the whole thing. I'm going to practice it. All right. I'll tell you what, in the interest of time, I'm debating whether or not we'll do that next one. Wait. Yeah, I think we'll skip it. Everybody, you can cross out the one about the Man riding a bicycle.
Okay.
Of course, you can always go home and do that one on your own, folks. We just won't do it in class. Okay, now you notice how those two word problems followed on the heels of the problem of 10.4 that said equations that will become quadratic in form. So you'll notice the original equation was not a quadratic, it was not a parabola, it was rational. But we turned it into a rational equation and we solved it. And so both of those word problems were like that. Rick and Juanita working together and the plane going with and against the wind. So now we're continuing with section 10.4, and I'm telling you that this equation is actually a quadratic in disguise. First of all, does it look like a quadratic?
No.
It doesn't look like a quadratic. And in fact, if I graph it, will it be a parabola? No, because it is not. It's not a parabola. Where is it? Oh, this is weird. X equals 32. I swear that they changed Desmos. I'm typing everything in the way I always have, and yet things are acting funny. Okay, well, here we go. Here's our graph. Does that look like a parabola? It's not a parabola. Does it have an x-intercept? Yes, one. Just one x-intercept. What does that tell us about the parabola? Well, it's either going to be a parabola that sits on the axis, like that, and so they would have the same solution sitting on the axis, or it's going to be a parabola that shares one solution there, but not both. So, for instance, it could be like that. So it would share a solution, but then the other one would be extraneous. So in any case, we're given this equation, which is not a quadratic. It does have an x-intercept. So we're going to transform that equation into a quadratic that shares that x-intercept and might have one extra extraneous root. So we just want to keep that in mind, that this equation really just has one x-intercept. So let's do it. How do we transform it into a quadratic?
Square root the s?
Square root the s?
Squared.
Square.
Yeah, square the s sounds good. Now, should we square the s? What was our previous technique? If you wanted to square a root, what do you have to do to the root first? Yeah, get it by itself. So I'm going to make it x if you don't mind, because I think s is a terrible variable. So x equals 32 plus 4 root x. In order to square the root, to get rid of it, we have to isolate the root. So how do we isolate the root? Move the 32 over. X minus 32 equals 4 root x. Do we really have to isolate the 4 out of there? I'm going to square this thing. Is it okay to leave the 4? It is actually okay. We can leave the 4. We just couldn't leave something being added to it, because then we'd have to FOIL, and that would cause a problem. But the 4 alone, that's fine. Let's go ahead and square both sides. Remember, the whole goal is to get rid of the square root, that pesky square root. And the only way to get rid of a square root is to square it. And so we needed the root by itself so that when we squared it, it would get rid of the root. So now, on the right, we have 16x. On the left, we get to factor or FOIL that. So the doublet square root rule says x squared minus 64x plus, I don't know, 964?
1024.
Oh, 1024 that is. Oh, I was way off. Okay, so x squared minus 64x plus 1024 equals 16x. Is that right?
Yeah.
All right. So a moment ago, I said if you're not sure how to solve a problem, a good starting place is to? Yeah, set it equal to 0. Move everything to one side. That's always a good idea, is get all your terms over to the left. So we minus the 16x minus the 16x. And now we have x squared minus 80x plus 1,024. Well, is that factorable? Now just imagine right now, the discriminant is actually helpful right here. Because do I want to start thinking about what numbers multiply to make 1,024? Not if I don't have to. So I'll do the discriminant real quick. The discriminant would be negative 80 squared minus 4ac. The great part here is that this can all be done in my calculator. So I type in the discriminant, negative 80 squared minus 4 times 1,024. And then that number, I just square root it to see if it's square rootable. And it is. This is square rootable. 2304 actually equals 48. So that means this thing is factorable. Because the discriminant was a square rootable number, that means this is factorable. So we do need to go ahead and figure out how to factor it. So what multiplies to make 1,024? It adds to 80. Whoops. Yeah, it adds to 80. Did I already show you guys how to make a factor table on your calculator?
Just keep dividing.
Yeah, if you guys want to follow along real quick, you go into your graphing component, your grapher. Okay, so you hit y equals. I wish I could show this on the screen. You hit y equals, and what you're going to type in is 1,024 divided by x. 1024 divided by x. That's the function you're typing. 1,024 divided by x. That's what you put on your y equals screen. And now we're not going to graph it. We're going to go to the table. And the table is the upper right-hand button. You have to hit second graph. Above the button graph is the word table. So you hit second table, and it should bring up a table of values for you. And that table of values is literally the factor table. It's literally the factor table for 1,024. And anytime there's a whole number, then that was a factor. So I've got 1 in 1,024, 2 in 512, 4 in 256. I can skip down past a lot of decimals. 8 and 128, skip down past a lot of decimals. 16 and 64, skip down past a lot of decimals. 32 and 32. And there we have it. If you followed along with that, great. If you didn't see how to do it, then let me show you after class. Because talk about a valuable time-saving technique to just have your calculator find all those numbers for you rather than having to do that yourself. So what is it? What adds up to 80?
64.
Yeah, 64 and 64. So there's our factoring, x minus 64, x minus 16. And so x equals 64 and 16. Now, remember, how many x-intercepts did our original equation have? Just one. So one of those is the real Slim Shady, and one of those is extraneous. Extraneous, I can't help myself. So which one's correct and which one's extraneous? Well, obviously from the graph, I can already tell the real one is 64. But I didn't know that if I didn't graph that. So let's just check them both. The equation was x equals 32 plus 4 root x. Now remember, we're only looking at the positive root of x. We're only looking at the positive root of x. So let's try 64 first. Does 64 equal 32 plus 4 times the square root of 64? So that'd be 32 plus 4 times 8, which is 32 plus 32, which is 64. Is that correct? Mm-hmm. Yeah, so 64 works. How about 16? Will x equal 32 plus 4 root x be true for 16? Well, can it even possibly work?
No, it's a 32.
There's already a 32 over there. So 16 can't possibly be equal to 32 plus something. So I can already tell that this is not going to work. But just for fun, I'll do it anyway. 32 plus 4 root 16. That's 16 equals 32 plus 4 times 4, which is 32 plus 16, which is what? 48? So, no, 16 is not equal to 48. So 16 is extraneous. It's extraneous because we only take the positive square root here because the square root was in an equation. And in an equation, you only take the positive square root. If we were allowed to take the negative square root, what would have happened? If I could have said the square root of 16 is negative 4, that would have been 32 minus 16. And what's 32 minus 16?
16.
16. So then it would have worked. And that's why the algebra gave that as a solution, because in algebra, a square root can have a plus or minus. But in an equation, it can't have a plus or minus. Okay, so that's it. Number 39 is going to be similar. Before we do it, let's go ahead and graph it, see what it looks like. 128x equals square root 1 minus 192x. Whoa. Ah, there it is. So there's our graph. How many x-intercepts does it have? Again, just one. So when we do this problem, we'll have to keep in mind that there's really only one solution. So let's do it. We start with 128y. I'm going to use x again. 128x equals 1 minus 192x. So how do we solve the problem? Yeah, you can wrap it in parentheses if you like. Yeah, I will on over here, and then over here we square it. Yeah, okay, good idea. I like parentheses. So now that gives us a really big number, 128.
163.
Yeah, 16384x squared equals just 1 minus 192x. And if we bring everything over to the left, 16384x squared plus 192x minus 1. Did I do that correctly? Moving everything to the left? Is this thing factorable?
Yeah.
How do you do?
Yeah.
That's a good way to do it. Yeah, so I mean, maybe, so what, you did the factor table? Or did you do the discriminant?
I did that.
All right, I'm going to do the discriminant real quick. Let's just see. B squared minus 4 times negative 1 times 16384. The discriminant is square rootable. So yeah, I calculated the discriminant. I took the square root. There was a whole number. So yes, this is factorable. So we would do the same trick, folks. If you want to go to y equals, you would type in 16384 divided by x. Is that what you did, Brandon?
Yeah.
Right, so then you go to your second graph or the table, and you'd have to just sit there and scroll down the list in order to find all of the numbers in that factor table. Folks, I don't think I'm going to give you a problem like this on the test, because this is needlessly laborious for checking on, how to do a skill. So 8 and 2048. Of course, with a graphing calculator, it's not that bad. All I have to do is scroll down and get all the whole number answers. Okay, it is that bad. 64 and 256. Okay, I wonder, do we have enough? Yeah, we do have enough. We're looking for two numbers that multiply to make 16384 that add to make 192. Did you notice something weird about this? I'm asking what numbers multiply to make this that add to make that. What's that? Yeah, normally you say what multiplies to make this that adds to make this. Well, what multiplies to make 1? Just 1 and 1. Are we allowed to say what multiplies to make this that adds to this? We've never done that before. So why are we allowed to do it? You could factor by grouping, I suppose. Yeah. There you go. Because you would do the first times the last, which would be this number times that number, which is there. And then you are technically factoring by grouping. So you multiply the first times the last, you get that. And then you find out what adds to make 192. It would be this. And then you'd have the 16384x squared. And then that would be plus 256x. And then plus negative 64x minus 1 equals 0. So yeah, you would factor by grouping. But when you're all done, you will find that it was those answers anyway. Wait, maybe not. Hold on, before I say that, let's keep going. So now factor by grouping. I've got this. 16384 divided by 256. So now that's 256x outside of x plus 64. And this one we can factor out a -1, so that's plus -1 outside of 64x plus 1. Wait a minute. Oh, I have that backwards. It's 64x plus 1. There we go. Yeah, so the factoring by grouping did work. And we ended up with 64x plus 1 times 256x minus 1. Boy, this is a very different type of problem. Because the numbers are so gigantic, and because you did have to factor by grouping, I don't think I'll put a problem like this on the test, folks. It goes a little above and beyond what's really necessary to demonstrate a skill. In any case, now that we have it factored, we would set this one equal to 0 and this one equal to 0. And therefore, x would be 1/64th, or x would be, sorry, negative 1/64th, or positive 1/256. And one of those is the answer. On Desmos, the answer is 0.0039. Which one is that?
164?
I think it's the one, yeah, it's the 1/256. Folks, I won't put something like this on the test. But yeah, that one was extraneous and that one was correct. I'll keep it like the one ahead of time. Those numbers were just so gigantic. All right, well, I heard my phone go off. So we're gonna pick up, no, I'm not gonna pick up. Larry Dieter is gonna pick up with you right here on number 40. So when he comes in on Tuesday, you can tell him that you left off on number 40. And yeah, but hey, let me just point out to you, number 40, because I do have a couple minutes. Larry is going to show you a very special process called, well, I'm going to call it U substitution. So number 40, folks. Let's look at number 40. We won't finish it, but we have time to look at it. I still have 4 more minutes. And number 40, does that look like a quadratic?
Yeah.
It looks like a quadratic. What's weird about it?
Something for it.
There. So you've got something squared plus 7 times something plus 12. So if I just covered up the 3 and minus 5, do you agree that it looks like a quadratic? Something squared plus 7 something plus 12? Well, that's actually the technique. You say, let's just go ahead and let u equal 3m minus 5. Instead of writing 3m minus 5 there and there, I'm just going to replace it with u. And so you say u squared plus 7u plus 12 is equal to 0. And just like that, you've transformed the equation from something nasty looking into just a normal quadratic. This is called u substitution. Instead of writing 3m minus 5, I'm just going to write u. Honestly, you can use any letter. You could use, well, not m, but you could use x or y. U is traditional when you get to a calculus class. We call it u substitution. So now, can you factor that?
Yeah.
Sure you can. That would just be u plus 3 times u plus 4. And therefore, what is u equal to? Yeah, -3, -4. So now guess what we do? Now that I've solved for u, yeah, I plug that back into the original. Instead of writing u here, I go back to writing 3m minus 5. So now I can say 3m minus 5 is equal to -3, or 3m minus 5 is equal to -4, and I keep solving for m, which was my original goal. So now here, I'd add the 5 over, so 3m equals 2, divide the 3 over, and my first solution is m equals 2/3. Here, I'd add the 5 over, so 3m equals 1, divide the 3 over, and m equals 1/3. This is really cool. I had a couple minutes, so I wanted to talk about it. And Larry will do it with you again on Tuesday. But this is cool because it's a two-step process. First, you take the quadratic they gave you, and you simplify it by replacing the 3m minus 5 with a single letter. And that's called u substitution. Then you solve a simpler quadratic, get your answer. And once you have your answer that u is equal to -3, -4, you go back to what you originally started with and finish solving those equations. It's really neat as far as the process goes. So, okay, what's that?
So for 41, you have to put everything on one side before you use the u substitution.
Right, yeah. You're going to replace, you're going to let u equal -3p plus 1, and then you move all the terms to the left, solve it like normal. And then when you're done, you replace u back equal to -3p plus 1.
Okay.
Okay, I guess I really am done now. I think I passed back papers to everybody. You're all good to go. Thank you very much. Jennifer. Thank you.
Yeah.